Okay, good morning. We now go back the chapter that I covered, the chapter that I skipped, integrals. Today I want to talk about primitive functions. You already learned about primitive functions and integrals in Math 3C. I do not consider any previous knowledge on the topic, but of course I have to go a little bit faster because we want to cover everything, okay? So, uh, the main concept going on is the notion of an integral. Okay, but today I don't want to talk about integrals, I will talk about primitive functions. So it will be a little bit disconnected why we are also interested in primitive functions. Primitive functions is the reverse process of differentiation. Okay, so for example, if I give you a function f, then you differentiate this function, and the product you get, what you get, is called the derivative. The process is differentiation. Primitive function is the reverse process. Okay, so you might ask why this is useful to do this reverse process. For the time being, consider it just as a mathematical curiosity. But then we learn about Newton's Leibniz theorem that is connecting essentially integrals to the notion of primitive functions. And integrals are extremely useful. For example, to calculate the areas, to calculate the volumes or things like that. And even in physics, for example, if you want to calculate the work of a variable force, you need to integrate. Okay, something like that. So integration is actually a very important tool, not only in mathematics, but in science as well. And the reason that we are interested in primitive functions, except from mathematical curiosity, is the connection that Newton's theorem established between integrals and primitive functions. But for the first or my 1 or 2 sessions, don't ask me why we are doing this. Just take it as a mathematical curiosity. So in differentiation, I give you a function, you do a process on it, you get a new function, which is called the derivative. Now, primitive functions, because of the integral, let me call it I. I want to go from a function f to a primitive function, which is called capital F. Okay, so this is the standard notation we use, yes? When I go to f under differentiation, the notation I use for the product, for the result I get, is denoted by f prime. And then usually for primitive functions, I give you a little function, you do the primitive function process finding, and what you get is denoted by the capital letter. So that's the standard. So one thing that already is clear for you, for example, let me give you a function x squared, and if I ask you to differentiate it, what do you get? You get 2x. But now let us this time give you 2x, and I ask you, can you tell me a function whose derivative is 2x? In other words, can you tell me the original function before the differentiation process has even started? So what is that? Okay, so then you will realize that x squared is not the only answer. Yes, so might be you can give me the answer x squared. That's correct. The derivative of this one is 2x, but you can also give me the answer x squared plus 1, because the derivative of x squared plus 1 is also 2x. Yes? And then, of course, immediately you realize how many answers you can provide. Infinitely many. So this is usual. They write x squared plus any constant that you can imagine. Okay? So that's what I want you to first learn, that if I go to in differentiation, when I give you one function, you definitely get exactly one answer. But when I give you a function in the process of finding primitive function, you get infinitely many functions back. But the good news is that it has been proven in a little bit higher mathematics that all those functions differ at most by an additive constant. So you might say that, okay, I know that the derivatives of these functions are all equal to 2x, but is it possible that there is a very complicated function so that when I differentiate using differentiation rules, miraculously something cancels out and I get 2x back? So this is not trivial. I want you to first understand. Of course, all these functions, the derivative is 2x, it is trivial to you, but it is not unreasonable to think that there might be another function that I cannot imagine, so that when I start differentiation process, it is so complicated, and the differentiation process becomes so complicated, it gives rise to different parts, and then different parts cancel out, and then I get with 2x. This is plausible. Do you feel that? There is no guarantee that these kinds of functions are the only functions whose derivative is 2x. But the good news is that no, mathematicians have already shown that there are no other solutions. So if you find one solution to the problem of finding primitive function, you already found all of them, because the difference between all of them is just one additive constant. Okay? It is not trivial. We cannot prove it. It needs a little bit. It's not hard, but it needs something more. But I want you to know that. Okay, so if I want to officially start the definition of a primitive function now, I would say that, so definition, this is something that you need to know. Yes, I would say that the function, let me write. Yes, the function capital F is a primitive function of little f if what happens? If what happens? Capital F prime is equal to what? Small. Yes? Okay, for example, as I told you here, for example, if I write capital F1 of x to be x squared, and if I give you f capital F sub 2x equals to x squared plus 1, these two functions are both primitive functions to the same function f of x equals to 2x. Yes, f1 of x and f2 of x, and then let us write little f of x is 2x. These two functions are primitive functions for the same function. Why? Because f1 prime is equal to f2 prime is equal to little f. Okay? Is that clear? Okay, so when I ask you to find a primitive function for a given function, what do I mean by that? I mean, give me a function whose derivative is equal to the function I gave you. That's it. Okay, and then of course we have to do the same thing we did for derivatives. Yes. So today I want to complete the table. This is the table in continuation of what you learned in Math 3C, because now we learn more functions to differentiate. So here I would, and then you will have two tables in the formula sheet, one for derivatives, one for primitive functions. So here I write little f and I write capital F. So if I ask you what is the logic, how do you think I will fill up that table? The same way I did it for derivatives, yes? So I started from the simplest possible type of functions, and then I start increasing the, I started to talk about different types of functions, so that other functions are combinations of those functions. Okay, so what was the first one in the list of derivatives, do you remember? Yes? Just, no, before that. Yes? A constant. Yes, so let me write a constant here. So it's a constant number. So what is the what is a primitive function for constants k? For example, if I give you 2, if I give you 3, if I give you square root of 2, and then I ask you the same question, give me a function whose derivative is 2, give me a function whose derivative is 3, give me a function whose derivative is square root of 2. So what are those functions? For the first one, what can I write? 2x, because its derivative is 2. For this one, I can write 3x. For this one, I can write square root of 2x. But of course, if they ask, this is also important to know, because there are 3 articles they use. I want you to understand them. They can sometimes say a primitive function, sometimes they can ask all primitive functions, and sometimes might be we will not be able to cover this lesson. They talk about the primitive functions, so I want you to understand about them. If they say all, this is not acceptable. You need to show me that you understand the meaning of the word all by putting a constant c there. So if they ask you find all primitive functions of 2, you have to show the respect to this and write 2x plus c. So this is all. If they say a primitive function, and it means that you should understand what is the meaning of a primitive function. It means that you are allowed to choose c whatever you like to, but don't write c, because if you write c, it means that you are writing all of them. Okay, so which choice is the suitable, the best one here? You can choose 1, you can choose 0, you can choose 10, you can choose the square root of 5, whatever. But which one is the best one? Probably 0. So if they say a primitive function, don't write c, it means that you chose c to be 0. Okay? If they say all primitive functions, you have to show respect to this article all, or this adverb also, that you have to write this constant c. And then about there, I will talk a little bit later. Okay? So here, when I write the formulas, I think in the formula sheet it consists that c. So here I would write what? Can you tell me now what happens? For 2 it was 2x, for 3 it was 3x, for square root of 2 it was the square root of 2x. So what is in general for k? Kx plus c. So let me use the same color. So it is kx plus c. Okay, what is next? Kx plus c. The next one, do you remember what was in the list? X to power, x was the, yes, x, let us talk about x. So, can you give me a function whose derivative is x? Yes? X squared is a good choice, but it is not that good. Why? Because if I take the derivative of this one, it gives me 2x, but I want to have x alone. So in anticipation of this coming, I put a 1/2 there to cancel that 2 coming down, yes? So I would write 1/2. Because when I differentiate this, 1/2 is a constant, and I differentiate it as I learned before, it becomes 2x, but the 2 that now comes down with 1/2 that I have here, cancel and I get x back. For example, if I give you, can you tell me x squared? A function whose derivative is x squared. Of course, it should be a 3rd degree polynomial, yes? So let us say x to the power of 3. But x to the power of 3 is not that good. Why? Because when I want to differentiate, 3 goes down, then it becomes 3x squared. So in anticipation that I don't need that 3, I put a 1/3 here there, so that when 3 comes down, it is cancelled. So in principle, if I continue and I ask you, can you tell me a function whose derivative is x to the power of n as integer, what is the answer? Yeah, it is 1/n plus 1, x to the power of n plus 1. Okay? So, but then here I want to write it like this. I would write x to power a, and then the answer becomes what? 1/a plus 1, x to the power of a plus 1 plus c. Okay, so let us prove this in general. I am claiming that this is the set of all primitive functions for this function. If I ask you to prove it or to show it, your duty is to differentiate the right-hand side and confirm that the derivatives becomes the left-hand side. Yes? So what I will do, I will take that function, whatever it is, and I differentiate. So, what we learned before, if I have the sum of two functions, I can differentiate. I will review more or less everything. So in principle, you need to think in this way. You don't have to write so much, but you differentiate the first part, you differentiate the second part, and then add. The derivative of a constant is what? 0. The derivative of this is a multiplicative constant, so I take 1/a plus 1 out, and then only concentrate on differentiating this part. To differentiate this part, the power goes down, and then x to the power of a plus 1, 1 unit less. That is the way that we differentiate. But then you see what happens, this a plus 1 and this a plus 1 are gone, and then 1 and 1 are gone, I get x to the power of a back. So that is the proof, okay? It is based on guesswork or whatever you like to. So we actually guessed a little bit about what should be the result, but then we confirmed that that is indeed correct. But immediately you see that there is some problem for this formula. This formula cannot work for one case. For which case is that? Yes? A is minus 1. Because if A is minus 1, I am in trouble. It becomes 1 over 0. So this formula does not work if A is minus 1. So for this formula to work, A shouldn't be minus 1. For the case A equals to minus 1, you didn't study that in Math 3C. But now in Math 4, you know about it, hopefully. Okay? Because if A is minus 1, what will happen? If A is minus 1, then my function x to power A is what?
1 over x.
Is x to power minus 1, which is 1 over x. So in principle, when A is minus 1, instead of x to power A, I can write 1 over x here. Yes? And then, do you remember? A function whose derivative is supposed to be 1 over x. This is not something you knew about in Math 3C. What was that? Probably you don't know it in Math 4 either. Yes? What was? ln of x. So that function was ln of x. Do you remember? ln of x, the derivative of ln of x that we studied before is 1 over x. Yes? And then, of course, ln of x does not make sense if x is negative. So I have to write that x is positive. So you see, this is Math 3C, Math 3C, this is Math 4. Okay, so we have. But let me stop here and then give you examples. Because there are a lot of examples that we can solve using only these three formulas. I want you to see all of them, more or less, the type of the problems that you're supposed to fix. Okay, but of course there are other formulas that I don't know, for some reason in the Origo book they don't even talk about this. Do you remember we had some relations like this? If I have two functions added and I want to differentiate it, what can I do? I can differentiate the first one, differentiate the second one, and then add them. That also is true for subtraction. But do you remember it was not true for what? It was not true for multiplication and division. Yes? It was also true if I have a constant number multiplied by a function derivative. I didn't need to differentiate this part, I can just differentiate the f part. Yes? So these rules, these three rules, have analogs in the primitive function. So I write it with I, okay? So I want you to write these things as well, so even though it is not in the book, but they are using it without mentioning it. So I means primitive function or integral. If I have two functions added, and I want to find a primitive function for the sum, I can do them separately. I can find a primitive function for the first one, I can find a primitive function for the second one, then I add the results. If that is minus, that is also minus. And if I want to find a primitive function of a constant number multiplied by a function f, I take c out, I don't care about the multiplicative constant, I just find a primitive function for my function and then multiply it by c. Again, don't push this analogy further, so if you think that you might have made a mistake, because I see many people still don't believe me, but anyway, I of f times g is not equal to I of ig multiplied. So if you think that you might make a mistake, write it and cross it over. So those formulas are completely generic formulas. Yes, it works for all types of functions, but these functions that you see are different types of functions because we will increase this. Yes, in Math 3C you had exponential functions, so and that was it. But here we have exponential functions. We will also have trigonometric functions involved. Okay, that we will learn. So let me write one example. This is the big example. So in which I cover from Math 3C to what you need now. Okay. So this is an important example. It doesn't mean it is hard, but it is important. So, and then because you learned about this constant c, it is annoying to put c all the time. So let me write determine a primitive function. A. primitive function. Okay, so now what we do, number one, let me start with very simple examples. Okay, so f of x is equal to, so let us write this. Okay, let me start with a very, very simple example. So x to the power of 2/3. So I want to find a function whose derivative is x to the power of 2/3. Okay, so do I need to do some changes? Because most of the these simple problems are the problems that you can immediately use the formulas. These are E-level questions. But the harder ones are the ones that you cannot immediately use the formulas. You have to adjust the form of the function in a way that is a combination of the functions that you have in the table so that you can use the formulas. Yes? So here, do I need to do any adjustments here? No, I can use immediately which row of the table? Second row, by giving the role of A to these 2/3. So what do? I will write the first few ones, but later I will do the most of the calculations in my head, so let us get used to it. I want you to do the same thing, okay? So what should I write? I will give the role of A to 2/3. I would write 1 over 2/3 plus 1, x to the power of 2/3 plus 1. These calculations, I want you to be able to do it in your head. Of course, if you write, it doesn't matter. Here, do I need to put a constant c here? No, because you have to show the respect that I have asked you for a primitive function. But then you shouldn't leave it like this. You have to simplify it. So 2 over 3, what happens? Let me do this simplification once. 2 over 3 plus 1 is what? 5 over 3. And then this is the same number, so it becomes 5 over 3. But here it is 1 over 5 over 3, which becomes 3 over 5, and then x to the power of 5 over 3. That's it. So if someone asks me, what did you find? I would say that I found a function so that when I differentiate it, it gives me this function. So that is what I did. Yes? Okay, so let us try to increase the level of difficulty a little bit. So number 2, for example, f of x is equal to, let me write square root of x. So can I differentiate it immediately? Sorry, can I find the primitive function immediately? The answer is no, because the square root of x is not in your table. So you have to adjust the form. So what can I do? It's very simple. So if you have forgotten these formulas, these are important. Let me write them down here. So if you have the second root of some box, whatever it is, you can write it as box to the power of 1/2. And then if you have the nth root of box to some power m, you can write it as box to the power of m over n. Okay, so these are very important for this part. Okay, so now what can I do here? I just use this formula first. So it becomes f of x is equal to x to the power of 1/2. Now this becomes the second row again, so I can immediately find the primitive function, a primitive function. How should I do that? I use the second row by giving the role of a to 1/2. Can you do it in your head? 1 over 1/2 plus 1. 1/2 plus 1 is what? 3 over 2. But 1 over 3 over 2 is 2 over 3. And x to the power of 1/2 plus 1. What? 3 over? Yes? Okay, but let me give you another example. So number 3, f of x is equal to, let me write 2x to the power of 3, the fifth root of x to the power of 2. So I want you to understand that it's not easy to guess a function whose derivative is this, even though we started with a little bit of guesswork. So don't underestimate the guesswork. The guesswork was a little bit a good one, because it enables me, as you will see now, to find a function whose derivative is this one, which is not easy at all to guess. Okay? So how should I do that? Yes?
The square root is x to the power of 2 over 5.
Mm-hmm.
And then when you multiply the x's, you get the...
You don't need to give me the details. I mean, they're not, the exponents are added. Yes, that's it. So what I want you to know, can I differentiate, can I find the primitive function for this and this separately? No, because of this one. So don't get confused. You are not allowed to take primitive function for this part and this part separately and multiply them, because that rule unfortunately does not work. So we have to do exactly what you said. So what I will do, I do not start finding the primitive function immediately because this function is not in my table. So I have to adjust its form. So what does it mean here? It means that let us write this multiplied by, I use this rule for the second one. So it becomes x to the power. This number goes to the numerator. This number goes to the denominator. So this becomes 2/5. Yes? But now I have two x's. I have two powers with the same bases. So I write the base and I add the exponents. So what happens? I copy and paste this 2. I write 1x here. I add the exponents. 3 plus 2/5. So what happens here now? So 5 times 3 is 15, 17 over 5. Yes? Now, is it ready to start? Yes. Which formula or formulas I need? Yes?
The second row of the table, and
Then this one. Both of them are needed. Why? Because it's a multiplicative constant. So it tells me that if I want to find a primitive function for that function, according to this rule first, I don't need to bother about multiplicative constant. I just put it there. So I put 2 there. And then I use that formula. Let me write it again here. So what is the formula? I use the second formula by giving the rule of a to 17 over 5. So it becomes 17 over 5 plus 1, x to the power of 17 over 5 plus 1. Yes? And then you do the calculations. So what is the answer here? It is 5 plus 17, 22. 1, 2, and 22 are cancelled. Remember, it will be 11, and 5 will go up. So it becomes 5 over 11. Yes? And then this is 22 over 5. So I hope that you agree it was not easy at all to come up with this guess, even though we started with the guesswork, but it was not easy to come up with this answer whose derivative is equal to this function. Is that clear? Okay, so let us go to the next one. So I want to increase the level of difficulty just to understand, to consider all cases. So for example, what is your opinion about this? So I write f of x equals to, for example, 2x to the power of 2, and then I have x to the power of 3 minus 2x to the power of 2. So what should I do about this? I want to find a function whose derivative is this function. Yes?
square the brackets.
And yeah, expand it. Yes, in principle. So yes. So what I will do, I will do this. I will write, still I don't start the process here. I want to simplify. So I would say the first one squared, 2 times the first one times the second one, and the second one squared. Okay? But it is not enough because I don't see that function there. And then you know that in derivative, even though this formula was wrong, we found the formula for it. Do you remember? It was the product rule. But there is no formula similar to that for primitive functions. Okay? So in any case, when you have a product, you don't know what to do unless you open it up. Okay? Because there are no product rule counterparts when it comes to primitive functions. So I will continue one step more. So it becomes 2x8 minus 8x to the power of 6 plus 8x to the power of 4. Now I want to find a primitive function for this. How many formulas I need from what I have written there? So you see, I have this difference and the sum of functions, so I need both of these versions. I have a multiplicative constant, so I also need this one. And for all these functions, I need the second row of my table. So let us just do it in one go because you have experience. Have you learned about them, yes, in matrices? Yes or no? Okay, so let us just do it. So here, what should I write? I write capital F. 2 is a multiplicative constant. What is x to the power of 8? X to the power of 8 is 1 over 9. 1 over 9 goes here. And then x to power 9. Yes? What is the next? Minus 8 is a multiplicative constant. X to power 6 becomes 1 over 7. So 7 goes down. And x to the power of 7. And the next one I have 8. X to the power of 1 over 5. X to the power of 5. That is the answer to this problem. Yes, is that right? Okay, now let us go to the next example. Number 5, let me write this. F of x is 5x to the power of 3 plus 3 over x. Okay, so what should I do? This you couldn't do it in matrice, not because it is hard, because it needs one extra formula that you didn't know about in matrice, and that is 1 over x. Yes? So the first thing comes to mind is to write it like this. Let me write it once, okay? You don't need, you can immediately start, but I want to make sure. How can I write 3 over x? 3 multiplied by 1 over x. You don't need to write it. I'm writing it because I want to make sure that you really understand what's going on. So then I can use the formulas. Which formulas? I need the sum formula because that is the sum of two functions. I need multiplicative constant formula because I have a multiplicative constant here and a multiplicative constant there. I need two formulas from my table. One formula is this one by giving the role of a to 3. One formula is, as you see, 1 over x, which is the third. So and then I combine everything. So what is the capital F? It is 5. X to power 3 becomes 1 over 4. 1 over 4 goes down. X to the power of 4. So what can I write here? Plus 3. What is the formula for the primitive function for 1 over x? Is just ln of x. But of course, in this case, x should be positive. If x is not positive, it doesn't. Any questions? Okay, now let us go a little bit further. So number 6. So let me write this formula. Are you following, or I'm going too fast? Because we have, yeah.
I just want to know, when we write an answer that has ln of x, should we specify that x can only be positive?
No. But you need to know that x should be positive. I don't know why they haven't mentioned that, because there is another formula. This is called ln of absolute value of x. It turns out that the derivative of ln of absolute value of x is also 1 over x. And that is better because it works for positive and negative values. Of course, it doesn't work for 0. And that is obvious because 1 over 0 does not make sense. So in principle, let me write it with blue. In principle, in university texts, if you have 1 over x, then they write ln of absolute value of x. This formula turns out to be true, and the only exception is, of course, evidently not 0. Okay? So this is the formula I prefer to write. I will check it out, but I think your book has written the previous one, emphasizing that. So in principle, if I want to solve it in university, I just write absolute value here. Yes.
Just still need the constant c.
Yeah, yes, thank you. because I am writing, by the way, I forgot to write the constancy here, thank you. And a constancy here, because here I am respecting to write all of them, yes? This is the formula I prefer to use all the time, but anyway. Okay, so now let me give you another example. F of x is equal, let me make it simple first. So 2x squared minus x plus 1 divided by 3x. So I want to find a function whose derivative is this. I hope that you understand, even though we started with guesswork, it is not easy at all to guess a function whose derivative is this function. So how can I do that? The ideas, I don't know, I gave you a similar example for differentiation. So if you have that, I also mentioned that is important there. And I'm more or less following the same type of functions there. Okay, so do you remember, I'm not talking about differentiation. If I ask you to differentiate this, there are two methods. Let us review a little bit because we were doing complex numbers for a long time. I hope that you haven't forgotten the derivative, yes? So we could do this in differentiation in two ways, okay? One way is,
You fill out 1 over 3x.
yes, so you can divide them separately, yes? But one way we also learned in math 4 later, which was,
Multiplied by 3x minus 1.
no, but I'm just asking you about the rule. It was called the quotient rule. If when I have a fraction, so you completely forgot about derivatives?
But you said that you didn't apply here, right?
No, I'm talking about derivative again. Okay? I hope I'm not here. I am asking you to find the primitive function. I know, but I told you this example that I am making now is very similar to an example that I made when I was teaching differentiation. And now I am just reviewing a little bit of lessons back then. So forget about this exercise, go back to the previous chapter, chapter 2, the derivatives. If I give you this function to differentiate, what do? There are two alternatives. One alternative that even Math 3 students could do is to divide this into 3 pieces and then do a step by step. But later in Math 4, we learned that if I have a fraction, I can use the quotient rule. Yes? But when it comes to primitive functions, only the first alternative works because there is no analog of quotient rule for primitive functions. Okay, so you have to do it in one way. Okay, so let us forget about what I said now. This is the continuation of the same example. I want to find a function whose derivative is this. So what should I do? There is no formula, there is no quotient formula for primitive functions. If you want, I can write this and cross it over. That is also, so you see, in derivatives, there were some alternatives to these. These are not the correct formulas, but in primitive functions, there are no formulas at all. Okay? So there is only one way for you to do it. So you just write f of x equals to this one divided by that one minus this one divided by that one plus 1 divided by that one. Yes? And then simplify it as much as you can. This can be written as 2/3 x to the power of 1. Here x and x are gone. I get minus 1/3. And here what I can do, I can write plus 1 over 3 times 1 over x. I don't need to adjust 1 over x because 1 over x is in my table. Yes, this is this thing. Yes? Okay, now what can I write? Let me write it here. So f of x becomes what? 2/3. What happens for x? X is this formula by giving the rule of a to 1 because here the power is 1. So what happens? It becomes 2/3 times 1 over 2 x to power 2. Yes, but 1 over 2 and 2 are simplified, so it becomes 1 over 3x to the power of. What happens for minus 1 over 3? Which row is that? The first row. It's a constant. If I have a constant, its primitive function becomes the constant multiplied by x. So what happens? It becomes my constant multiplied by x. And then this is 1/3. And 1 over x becomes what? ln of x. But again, assuming that x is positive. Is that right? Okay. So let me give you 2 more examples I want to wait for you. Because if you can solve these 2, probably you understood whatever you need to understand so far. Okay, so let me write 2 more examples here and wait for you. So that was number 6. Let us write number 7. Okay, what do you think about this function? F of x equals to 5x to the power of 3 minus 2x to the power of 4. Let me decide about this. I would write it as 3 x to the power of 2. Okay, and then I would write plus 2x squared plus x minus 1. Okay, you can start doing this. I will write one more for you, okay? So let us do the first one, number 7. I hope that you understand that this is more or less the same thing. So I will start adjusting the form. So I would write 5x to the third divided by 3x squared. And then I have minus 2x for 3x squared. And then I have 2x squared over 3x squared. And then I have plus x over 3x squared minus 1 over 3x squared. Yes? Okay, so then the next step is still simplification. So this can be written as 5 over 3. Write it in a way that you can see the multiplicative constant transparently. Then this becomes x. Here I would write minus 2/3, and then this becomes x to the power of 2. Here this is only 2/3 left. Here what happens? It becomes 1 over 3, but 1x lives in the denominator. I write it 1 over x. 1 over x is an exception, so remember, whenever 1 over x appears, leave it like this. But what about this one? So here I write it as minus 1 over 3. If I insist to write this, then I am in trouble. Why? Because 1 over x squared is not in the table. 1 over x is the only one in the table. So remember about the exception of 1 over x in Math 4. 1 over x should be kept as it is. But what can I do for this one? Negative 2. So be careful. The only one that you have to keep it exactly as it is 1 over x. If I have 1 over x squared, 1 over x squared is not in the table. So what you do, you bring it up here. And then continue, okay? Which formulas are involved? Addition, subtraction, multiplicative constant formulas down there. And then this one, and this one, and that one are all second row, and this one is the third row, and this one is the first row. So it's a combination of all the formulas that we have in one problem, yes? So this becomes now capital F of x is equal to x is 1 over 2x squared, 1 over 2 multiplied here. This becomes 1/3 x to the power of 3, 1/3 multiplied here is 2 over 9, x to the power of 3. 2 over 3 is the first row, it's a constant, so the answer becomes 2/3 x. This becomes 1 over 3 ln of x. But what about this one? Let me write it here once for you. X to the power of -2, it goes to 1 over -2 plus 1. X to the power of -2 plus 1. I'm using the second row formula. But this becomes what? -2 plus 1 is -1. So 1 over -1, x to the power of -1. This becomes simply -1. So it becomes minus x to the power of -1. But I prefer to write it with positive exponent. But it is not a have to. You can just stop there. So the answer to this part, according to the second row formula, is -1 over x. I have a minus a third there. So it becomes plus 1 over 3x. So that is the answer. How many of you got the same answer? Not that many. Why? So what was the problem? Was it hard? Yes. If you don't understand something, please let me know, okay? Is that okay? Yes? Okay. Now the next one is a little bit harder, but it is manageable. You have to be patient. Of course, patience is not enough. You also need to like it, you know. So how much you want to be patient? Yes. Okay, so let us start doing it. But what is your suggestion for me? It's a combination of all these problems we have learned so far, yes? First of all, I see a fraction. I know that there are no rules for fractions when it comes to primitive functions. So what I need to do, I need to separate them, yes? But then I have squares involved, so I have to use those red formulas. Unfortunately, I cleaned them. But let us just do it together. So the first thing I will do is to write f of x is equal to 5x squared divided by 2x. And let us save some time. You know that eventually, what should I write for the third root? X to the power of 1 over 3. So let us save a little bit of time. And then I will have plus 3. Instead of square root of x, I write x to the power of 1/2 divided the same thing. Exactly. And finally, minus 1 over 2x, x to the power of 1/3. And the rest of it is math 1c, to be honest, because that is simplifications. Yeah, so what should I do? This is 5 over 2. I write it in a way that it becomes transparent. And you do this in your head. I have x to the power of 2. I have 1x here, 1x to the power of 1/3 there. So one of these x's and one of those x's are gone. Then it becomes x to power 1 divided by x to power 1 over 3. So I have to subtract the exponents. So it becomes x to the power of 1 minus 1/3, which is 2/3. Yes? So it becomes x to the power of 2/3. Okay, can you do the other one in your head? So 3 over 2 is the multiplicative constant. Can you do these numbers in your head? Exactly. X to the power of minus 5 over 6. Do you want me go through it? Let me just do one more here. That's the only one. Okay, so what I will do, I would write this one and that one are multiplication. So what I will do, I would write x. This exponent is on top, so I write 1/2. But the exponent of this one and that one are in the denominator, so I bring them with negative values. Yes, that's it. And then I have to calculate this simple number. I take the common denominator 3 times, it becomes 3. And then this to this 6 times, so it becomes minus 6. This to this 2 times, it becomes minus 2. So it becomes minus 8 plus 3 is minus 5 over 6. Yes, that's correct. Yes. And the next one is even simpler. So I write minus 1 over 2. 1 and 1 over 3 are combined. It becomes 1 plus 1 over 3, which is 4 over 3. I bring it up. It becomes minus 4. Yes. And then I need to find a primitive function now. Everything is ready. So 5 over 2, 1 over, so let me write this one for you. So I would write 1 over 2/3 plus 1, x to the power of 2/3 plus 1. But this becomes 5 over 3, which becomes 3 over 5, x to the power of 5 over 3. Yes? But these 3, yes?
On that last one, I didn't understand.
Here, 1 plus 1 over 3 is 4 over 3. But x to the power of 4 over 3, I bring it up, make it minus 4 over 3. Yes? So here I have this number, and I have 5 over 3 here. 5 over 3 multiplied here, 5 and 5 are cancelled, so it becomes 3 over 2. X to the power of 2 over 3. Okay, so let me, I don't know, because these things, I feel you are not very comfortable with these kinds of calculations, but in principle they are not hard. So here I have, let me write this once. So 3 over 2 multiplied by 1 over minus 5 over 6 plus 1, x to the power of minus 5 over 6 plus 1. Yes? So you see I am doing the middle one. 3 over 2 is a multiplicative constant, and I am using the second row formula by giving the role of a to this minus 5 over 6. So it becomes 1 over minus 5 over 6 plus 1, x to the power of minus 5 over 6 plus 1. But what is this number? 1 over 6. 1 over 1 over 6 is 6. 6, 18 divided by 2, 9. Yes? And then I have x to the power of 1 over 6. So that is what I have to write here. Okay, the next one. So let me write it again. Minus 1 over 2. And then I use the same formula. 1 over minus 4 over 3 plus 1, x to the power of minus 4 over 3 plus 1. Minus 4 over 3 plus 1, what is the answer? Minus 1/3. 1 over minus 1/3 becomes minus 3. Minus 3 multiplied here is 3 over 2. So it becomes 3 over 2, x to the power of minus 1 over 3. So I will write it there. So it becomes plus 3 over 2, x to the power of minus 1 over 3. And that's the final answer. I don't think you will face this level problem, but don't consider this a hard problem. This is a combination of a lot of problems in one problem. Yes?
What did you do on the 3 over 2?
Here?
Yeah, no, on the right part of the word.
Here? Here?
That,
Here?
Yes.
I didn't consider, you mean?
It was
This was...
right? At the beginning. Above it.
Okay. I did it in my head, or I did. No, I did it in my head, I think. Yes. So here I have 5 over 2. Yes. And then I would write 1 over 2 over 3 plus 1, x to the power of 2 over 3 plus 1. Yes. And then 2 over 3 plus 1 is 5 over 3. So it becomes 3 over 5. 5 and 5 are cancelled, so 3 over 2. Yes, so that's 3 over 2. Is that your question?
Yes. But then we have 2 over 3 plus 1 over the x.
Okay. Thank you very much. Thank you. Yes, I forgot to write that. Yes, thank you very much. You mean this one?
Yeah.
Yes. Thank you very much. It's 5 over 3. I don't know. Yes. Yeah, I accidentally wrote the same number. Thank you very much for the thing. Thank you. Okay, any questions? But there are some harder problems in the book, not from calculation. This is a hard calculationally hard problem. It's computationally lengthy, but it's not hard. But let me ask your opinion about this without telling you anything. Okay? So if I give you number 9 and 10, probably will be the level 3 problems. So it is not as complicated as this one, but you need to be observant a little bit. So number 9, if I write a function, what is your opinion about this? Of course, because you don't have the formulas of derivatives in your memory, you might be a little bit in trouble. So this one. So let me put a star here. So when you are studying for the national exam, be careful, there is a point in this which is not standard. So what do you think will be a primitive function for this function? A function whose derivative becomes this function. So I hope that you understand that the previous method is not working. Yes? Because if it was the other way around, yes, you can do the same method, but here you cannot do anything. You cannot say 2x over x squared plus 2x over 1. Yes? This is not possible. So what should we do? Yeah, make a mark here. So I will give you a little bit of hint. Do you remember this combination or not? I mean, if you don't remember, of course, there is no way for you to understand that. Do you think that this combination looks familiar? A fraction whose denominator what it is, its numerator is the derivative of the denominator. It appears somewhere. And of course, if you are good in chain rule, in principle you should be, there is something on the board that you can immediately understand. What is this combination? Let me write it in this way for you. Yes? Yes. You remember, if I ask you what is the derivative of ln of x, you have it on the board. But if x, instead of x, I have u, which is a function of x, do you remember? That's the chain rule. So I told you that if you have u instead of x, u itself is a function of x, you follow as if it is x. It means you write 1 over u, but this is not finished because you have to multiply by an extra u prime because of the chain rule. Yes? So then if I write it in that way, it becomes u prime over u. So I want you to see, I want you to remember this when you are reviewing for the exam. Remember this combination as well. If you have a fraction, but not any fraction, a fraction whose denominator can be anything, but its numerator should be the derivative of the denominator, this is already indicating that a primitive function is a ln function. Okay? So here, so let me write this as a remark. So write like that. A primitive function I of this combination is what? ln. Yes, so write this somewhere. It is not in the formula sheet, but there are some problems in the book, and I have seen problems in the national exam. You might be able to use this. So let me clean this and ask your opinion. Do you agree that this is the same combination? Because it's a fraction, so that its numerator is the derivative of the denominator. So this is exactly u prime over u. But what is playing the role of u in my problem? X squared plus 1. So that's it. So if I ask you, you have to explain. So let me write it in a way that it is good to write it in the national exam. So you write f of x equals to, you write x squared plus 1. Instead of 2x, write x squared plus 1 prime. Yes? Because the derivative of x squared plus 1 is indeed 2x. And then you say that f of x is equal to, can you tell me what's the answer then? Yes, because this is playing the role of u. So this becomes ln of x squared plus 1. Okay, so in all these examples, mainly this is Math 3C. This is the new one, very new one. I mean, it was not computationally hard, but you need to know the point, otherwise you will not be able to solve it. Okay, let me ask you another question now. Let us play around with this concept a little bit. So I give you this function now, f of x. What do you think about this? I write x to the power of 3 plus 2, but here I write x squared. That is not exactly that combination, but if you understood the point, you should be able to solve that problem as well. Do you see that this is not identical to the previous problem? Because if I take this to be u in my head, what will be u prime? What will be u prime? 3x squared. Unfortunately, I don't have that 3 there. So what do you think I will do first? So I would write 1/3 and put 3 there. That's the whole thing, exactly. So what you do first, you write f of x equals to, you need your 3 there, so I would write it there, but I'm not able just to bring something out of the blue and put there unless I compensate for that change. Yes? But now the good news is that this is not an obstacle at all, because that's a multiplicative constant. So it doesn't play that much role. I just write it and multiply it by my answer. So now everything is ready. Can you tell me what the answer is? I want to find the primitive function. So I will continue a little bit more for you here. So it becomes x to the power of 3 plus 2. And in the numerator, I would write x to the power of 3 plus 2 prime. I hope that everyone agrees that what I have written here now is exactly the same function I had here. Why? Because I take the derivative of this, it becomes 3x squared. The 3 and 3 are cancelled. I get x squared, and the denominator is exactly the same. But why I did this? Because I want to use somehow this fact. Okay, now can you tell me what is the primitive function? 1/3 is a multiplicative constant, so I write it here. And I find a primitive function only for this part. What is that? ln of x to the power of 3 plus 2. That's the answer. Yes? Okay, let me give you a little bit more interesting problem. So number 11. So number 11, I want to wait for you. So 11, that is a little bit surprising result, I think. I want a function whose derivative becomes tangent of x. Yes? The same, you see that is number 9, number 10, number 11. The same question. I'll wait for you a little bit. Would you solve it? Yes, how?
The word tangent, the tan has sine over
Cosine, yes. So you might not be able to guess that a function whose derivative is tangent is this function that we're supposed to find now. So what you write, f of x is equal to sine x over x. That's the definition of tangent. But the definition of the tangent, do you agree? It is very similar to this combination, except for a minus sign. Yes? Because this is the denominator. What is the derivative of the denominator? Is not exactly sine. That problem is in the book. It's not exactly sine, is negative sine. Okay, but you unfortunately have sine. But these negative signs or these multiplicative constants are easy to fix. Yes, so what we do first, I write minus sin because I need minus sin, but I have to compensate for that change that I made by putting an extra minus sign here as well. Yes? Now, if you give the role of this to u, the numerator becomes exactly u prime. So it is u prime over u again. So what is a primitive function? Minus sign is minus sign. U prime over u becomes ln of u, which is cosine x. So might be it's a little bit surprising. The function whose derivative is tangent has something to do with logarithm function. Yeah, so it's minus ln of absolute value of x. In principle, I should write absolute value of cosine x, but you need to consider that cosine is positive. Okay, So now if you want to be creative, let us see how many of you can solve this problem. Okay, so number 2, I haven't seen these type of questions, but this is exactly the same topic. So I will write this, and this is the end of the story today, yes? The end of the show will come next week probably. Okay, so this. I will wait for you a little bit. Of course, when I write like this, I mean x is positive, yes? Let me give you a hint, okay? How can I give you a hint? Okay, might be, it is a little bit strange, but write x to be square root of x times square root of x. Because first of all, it is valid. If x is positive, square root of x times square root of x is x. But how do you think this will help you to solve the problem? Again, I'm saying I haven't seen this quite in the national exam or something, but this question is in the book, similar question is in the book. So if you don't mind, let me put a star on all of them when you want to review. How this will help me, let me tell you, okay? So this becomes 1 over square root of x, as I told you. But why do you think this might be a good hint? Yes?
Right, square root of x cubed.
Cubed? No, because this is not a product. Yes? But why do you think it is useful if there is anything to with it? Yes, if there is something useful with it. What do you think I will do next?
Factorize.
Yes, exactly. I factor it out. What happens? This. But can you see the next step? The next step, first of all, I don't know, do you agree that I can write like this? Yes or no? You see, if you are not very comfortable with this, your algebra is not that strong. So you have to make it up, you bring it up, promote your algebra. Is that okay? Because if I ask you A over B over C, what do you write immediately? A over BC, yes? So 1 over A, so A over B time over C. So it should be A, B, C. So this will be multiplied here. So what I have done is legal, yes? But what is beneficial here? Is it U prime U combination? With a little minor difference, yes? What is that? Do you remember? The derivative of square root of x is what? I told you it is famous. Square root of x, the derivative is what? 1 over 2 square root of x. So if I take this u, this is not exactly u prime, but I can fix it. Yes? I put a 2 here, and I multiply by a 2. Now that's exactly the combination, yes? Because this becomes what? U, and this becomes u prime. So that's it. So the primitive function becomes what? I have a factor of 2, and I write ln of square root of x plus 1. That's it. Yes? So I don't expect you to be able to solve these type of problems, but I would expect you be able to solve it by giving you the hint. Okay? So, yeah, anyway. So this is a crash review of matrix and 2 new formulas, 1 over x and 1 this combination. So I will consider 9, 10, 11, and 12 hard problems. Even though they are not computationally hard, but might be, if you don't know the point, you will not be able to solve it. Any questions? Thank you.